Hello, everyone. My name is Fatima Alsakka. I'm a PhD student at the University of Alberta. It's right behind me. I pre-recorded my presentation because it's currently 4 a.m. in my time zone. I really hope you enjoy my presentation. Today, I'm going to present our study on evaluation and comparison of the performance of artificial intelligence algorithms in predicting construction safety incidents, a study conducted by Dr. Yasser Mohamed, Dr. Mohamed Al-Hussein, and myself. Our outline for today looks as follows. We'll start with the background, the problem description, and study objectives. Then I'll walk you through the data mining process we conducted. We'll discuss the results, and we'll finish this presentation with a few concluding points. Now, we all know that construction projects involve a lot of high-risk activities during which safety incidents may occur. In Canada, hundreds of deaths and tens of thousands of injuries on construction sites were recorded during a period of 11 years. Healthcare expenditures reach billions of dollars every year. And of course, when we talk about billions of dollars, we talk about contractors becoming more concerned about safety risks. Now, thanks to modern technology, large volumes of data are being collected every day. This allows deploying artificial intelligence and machine learning models to predict the possible outcomes of safety incidents and take corresponding protective measures. However, different algorithms can vary in performance, and the metrics used to evaluate the algorithms could misleadingly indicate a satisfactory performance when it's not the case. So, for example, is the accuracy of my predictions really 90%, or is there something behind it? Here we are talking about potential bias in evaluating the performance. This issue is manifest in a study that aimed at predicting safety incidents severity. The data set used was complex and heterogeneous, and so the authors used a clustering analysis to try to deal with this issue. However, the results still showed high values of error, where they reached 60% in the case of their best performing model. Still, the study relied on an 18% error to judge the performance of the algorithms, which was biased due to a high degree of imbalance found in the data. In light of this, the aim of this study is to train a set of machine learning models to predict the severity level of safety incidents using the same data set, while mainly highlighting the importance of a proper performance evaluation, compare the performance of different algorithms, of course, and identify the best performing algorithm. Now, this data set we're talking about includes 60 different attributes that are classified into 9 categories, including time, day, experience, activities, age, occupation, etc. And we're also talking about 6 different levels of severity, including level 1, which is at-risk behavior near miss, level 2, accident with material damage, up until level 6, which includes fatalities. So we trained 2 sets of prediction models, one for numerical estimation and one for classification of the severity levels, of course. Now, let's talk about the data mining process we followed. We started by cleaning the data, but the data was tidy and did not require significant cleansing. Only 4 instances were removed due to missing values, and 200 outliers were identified and removed using density-based outlier detection. We must note at this point that this data set is highly imbalanced, which means that some classes had a significantly higher frequency than others, as you can see in this histogram. This imbalance in the data set could result in building inaccurate models that show satisfactory performance. 2 of the techniques used for dealing with imbalance which are typically used, are oversampling, which means duplicating instances from the minority classes, or undersampling, which means taking subsets of the majority classes. And so we tried both. This is the set of the machine learning models that we trained and tested. And for the numerical estimation, we trained support vector machine, linear regression, and gradient boosted trees. As for the classification problem, we trained k-nearest neighbor, also GBT, random forest, and generalized linear model. We used RapidMiner to train and test the machine learning models, and 80% of our data was used to train the models using a 10-fold cross-validation, while the remaining 20% was used to test and validate the models. These are the evaluation metrics that we used in our study. For the numerical estimation, we used the mean absolute percentage error and the root mean squared error. As for classification, we used accuracy and the classification error. However, of course, we should compute the values of recall and precision to better understand accuracy. When we talk about recall in this case, we ask ourselves, among the safety incidents that will actually occur, how many are we able to predict using our models? We do not want to miss predicting an incident that involves human losses. As for precision, we ask ourselves, among the incidents that are predicted to occur, how many will actually occur? And again, we really don't want to predict that 100 incidents will occur when only 5 incidents take place. This is literally a waste of money, time, and effort. Now let's discuss the results of this study. The results of oversampling and undersampling techniques were not favorable, and this is because there are large gaps between the frequencies of classes. Undersampling significantly reduced the size of the data set and resulted in poor performance. Meanwhile, oversampling introduced the problem of overfitting, since duplicates started appearing in the training dataset and the testing dataset. As such, the dataset was used as is, and the models were rather evaluated against each other. Now, this table summarizes the values of the performance evaluation measures. For the numerical estimation, LR had the highest MAPE value. As for class prediction, RF had the highest error. Moreover, it's interesting to note that for the RF model, the class recall was 99.75%, which is almost 100% for level 3, and 0.28% for level 4. This means that this model performed really poor because of the problem of imbalance, and it failed to predict level 4 incidents, which include those necessitating medical intervention, and this is critical. Therefore, the LR and RF models were excluded at this stage. Now, during validation, the trained models again did not yield promising results, as the error reached 37% in case of the class prediction models. And again, by now we know that this is due to the problem of imbalance, the severe problem of imbalance that we have. Now, for the numerical estimation, if we base our decision on MAPE values, would select SVM as the best performing model. However, if we base our decision on RMSE, would select GBT. However, for the purpose of comparison with the results of the previous study, and since they used MAPE to judge the performance of their algorithms, we went for the SVM model. As for the class prediction, KNN exhibited the best performance, and thus was selected. However, satisfactory values of error computed for the whole dataset does not guarantee a good performance of the models. We computed the error values for each class separately, and we got the following results. SVM and KNN performed poorly in predicting level 1 incidents, while the errors were almost 0% for class T. Imbalance again. So the reasonably acceptable performance of the models is a result of the misleadingly low error in level 3 predictions. Given the high degree of imbalance in the data set, we could see that predicting that if any new instance belongs to level 3 class, this would give us relatively acceptable results as compared to the models that we currently have. In fact, the performance of the selected models was only slightly better than that of the zero rule classifier, as shown in the green bars in this histogram. Based on the results of this study, we can conclude the following. The perception of the performance of machine learning algorithms could be highly biased depending on the metrics used for performance evaluation. The quality of the training dataset could diminish the value of deploying some advanced machine learning algorithms. Simpler classifiers become more desirable. And finally, when the quality of the data set is questionable, it's critical to perform multiple levels of performance evaluation to confirm the credibility of the evaluation results. Thank you very much. I look forward to your questions.